The last concepts that we need to cover in D.1 on stellar quantities is about luminosity and apparent brightness. Now, luminosity is a fairly straightforward sort of term, really. If you think about it, luminosity, it's about how luminous an object is. But we need to be a little bit more specific than that. And luminosity is considered to be the total energy that's being radiated from a star. And when we say total energy, we mean sort of all forms of electromagnetic radiation and in all directions. And it's the amount of energy radiated per second. And if you think about that, if it's energy per second, that's sort of the same as power in a sense. And so as a result, luminosity is measured in watts. So the idea here is that because we are looking at how bright the star is or how luminous it is, we can't actually measure or can't directly measure what luminosity is, because we can't sort of capture all of the energy that's being radiated from the star. We can only see it from our vantage point in space. So we can't directly determine a star's luminosity. So we need to be able to make some other measurements in order to be able to determine how luminous a star actually is. So we can't measure its luminosity, but we can measure its apparent brightness. And when we're talking apparent brightness, as the name suggests, it's how bright it appears to be. So if you think about apparent brightness, easiest way to imagine it is imagine if you've got someone standing there with a torch. If they are standing a long way away, then the torch doesn't really look that bright to you. If they're standing a fair bit closer, then the torch looks really bright. Similarly, if you were to have a torch that, like a fairly cheap torch, that wasn't that bright, if it was really close to you, it wouldn't necessarily be that great. But if you had a torch, a much more expensive torch, and you were standing close to it, then it would appear to be even brighter. So that leads us to two aspects about apparent brightness that are important to discuss. And you can see there, as I've just written, when we're looking at apparent brightness, we're measuring watts per square meter. And if you think back to Unit 4, if you're looking at an area, a power over an area, that actually relates to an intensity. So when we're looking at apparent brightness, we're really kind of looking at the intensity of the light that's being radiated. So effectively, this idea of apparent brightness really comes back to that equation I equals P on A, where I is going to be the apparent brightness B and P will be the luminosity L. Before we go into that, though, as I was just sort of alluding to, the more luminous a star, so if we've got a star that's radiating more energy per second, then it makes sense that the apparent brightness will be greater. So we can express that as a relationship, and that relationship would be directly proportional. So we could write that B is proportional to L, and similarly, the further away a star is from Earth, the less bright it will be, and that's going to follow a inverse square proportion. Now, when we're talking this idea of brightness, keep in mind it is the apparent brightness. The less bright it will be. It's the apparent brightness that we're interested in, not necessarily the luminosity as such. So we're going to make some measurements that determine something about the brightness, and we can then link that back to the luminosity. So if we combine those two, and it's similar to the equation for intensity, as I said, the brightness then is given by the luminosity divided by 4 pi d squared. So basically we're just looking at the amount of energy that's radiated over the spherical surface that the energy is being radiated over by the time it has reached Earth. So this equation is now useful in that if we can measure B, so if we can measure the apparent brightness of a star as we see it in the night sky, and we could perhaps find the distance to the star using stellar parallax, that means we can actually then calculate the luminosity of the star. Conversely, if we happen to know that luminosity because that particular star is similar to others of a known luminosity, and we can measure then the apparent brightness, we can then calculate what the distance to that star is. So useful sort of in both directions there in order to calculate something about the distance to the star and its luminosity itself. Now another aspect to consider about stars here that's important is about black body radiation. Now that's covered more fully in subtopic 8.2 on thermal energy transfer, so I'm not going to go into it in lots of detail here. I'll just sort of link back to the key ideas, and the main thing to remember about black bodies is that they're sort of idealized objects. By idealized we mean that they sort of do things perfectly. So they're idealized absorbers of all electromagnetic radiation. So what we mean by that is that they any electromagnetic radiation that falls upon them, they will absorb it, they won't reflect any of it. But because they've absorbed it all, they will then be able to re-radiate that energy as well. So there's a difference between reflecting and re-radiating, and so the reason why it's important that we make that distinction is that if it's reflecting it, then the incoming radiation is the same as the outgoing. If it's re-radiating it, the spectrum of the re-radiated energy can be different, and in this case the spectrum, and we're talking by spectrum, we're talking the electromagnetic radiation that's released from it. So the spectrum of the radiated energy will be determined by the temperature of the object itself. So that's an important thing to consider when we're dealing with stars, and the reason for that is that we can correct that word, depends on the body's temperature. The reason why it's important to relate to stars is that we can consider stars to be fairly good approximations to black bodies. They're not perfect, so they're not entirely considerable to be black body objects. They are pretty close to it, so that we can identify that they are capable of emitting all wavelengths of electromagnetic radiation. So because they can emit all of those wavelengths of electromagnetic radiation, they're close to being black bodies, and so we can treat them accordingly. And for this next little bit again, more detail in subtopic 8.2. I'm just going to gloss over it a little bit here by just stating that stars then are going to follow the Stefan-Boltzmann law. And that basically means that we can map the temperature of an object to the luminosity of the object itself. So when we're dealing with stars, the equation that we're interested in there is the luminosity is equal to sigma a t to the power of 4. Again, refer to subtopic 8.2 for a bit more detail on that particular equation. So looking at the quantities there, we've already seen what L relates to. That's the luminosity of the star. And luminosity, it's missing O there, sorry. Luminosity is measured in watts. So again, remember here that if it's measured in watts, it's basically a power kind of idea. Now the value of sigma here is the Stefan-Boltzmann constant. And that has a particular value. So think of it as just being a constant that is applicable to this particular relationship. It has a value of 5.67 times 10 to the negative 8 watts per square meter per Kelvin to the power of 4. And A is the area, or the surface area of the star. And when we're dealing with surface areas, we know that they're measured in square meters. And T is the temperature of the star in Kelvin. So there's the relationship for the Stefan-Boltzmann constant as it applies to stars. Now, if we just take this one little step further, if we approximate the star as being a sphere, now when we consider most stars, they are pretty close to being spherical. And that then means that we can do something with the area, as being spherical. That means that the area here is then given by the equation 4 pi r squared, so that's the surface area of a sphere. That then means that we can change that equation and instead write it as, so if we substitute that in for area, so 4 pi r squared t to the power of 4. That means that luminosity is dependent on two quantities of the star. And you can see from that equation, luminosity depends on a star's size. And here we're talking about the radius of the star, or you could consider the surface area of the star, and its temperature. Now we'll take a bit more of a look at those ideas as we go into subtopic 8.2, where we'll have a look at actually classifying stars, and that relates back to both their temperature and their size, and a few other quantities in there as well.